Hello everyone, and I hope you're having a great day. Have you ever wondered how discarded oil drums can be transformed into strong railway tracks used in modern transportation? In this video, we will explore the full industrial process that turns metal waste into high-strength steel rails through advanced recycling technology. By the end of the video, you will also learn how these railway tracks are used in real life and why their quality is so important. Before we begin, let me know in the comments, which country are you watching from and what time is it there right now? The primary raw materials for this process come from used oil drums collected from industrial zones, transportation depots, and large storage facilities. These steel containers, once used for storing fuel or lubricants, are gathered through organized recycling networks designed to reduce environmental impact. Each drum represents a significant amount of reusable metal that can be recovered and processed into new engineering materials. Surprisingly, recycling steel can save up to 70% of the energy required compared to producing steel from raw iron ore. In my opinion, this stage highlights the importance of sustainable resource management in modern manufacturing. Before entering the processing line, these materials must first be sorted and prepared carefully to ensure quality consistency throughout the entire production cycle. Before the oil drums can be transformed into high-quality steel, they must undergo a thorough cleaning and preparation process. Residual oil, coatings, and contaminants are carefully removed using industrial washing systems and chemical treatments designed to meet strict safety standards. This stage ensures that impurities do not interfere with the metallurgical properties of the final product. Interestingly, even small amounts of contamination can significantly affect the strength and durability of steel structures. What I personally find fascinating about this stage is the precision required to maintain material purity before melting begins. But what happens in the next stage is where the real transformation begins, as solid steel waste prepares to become liquid metal. Once cleaned, the oil drums are mechanically processed into smaller steel pieces suitable for melting. Powerful hydraulic cutters and industrial shredders break down large metal containers into manageable fragments that can be efficiently transported through the production system. This mechanical preparation ensures uniform heating and improves energy efficiency during the melting stage. An interesting fact is that reducing scrap size significantly increases the melting rate, helping factories maintain continuous production output. In my opinion, this stage demonstrates how engineering optimization improves both productivity and sustainability in heavy industry. With the material now properly prepared, the next step introduces intense heat that fundamentally changes the structure of the metal. At this stage, the prepared steel fragments are exposed to extremely high temperatures inside electric arc furnaces capable of reaching over 1,600 degrees Celsius. Powerful electrical currents generate intense arcs that rapidly melt the recycled metal into a glowing liquid state. The heat is carefully controlled to maintain consistent chemical composition and prevent structural weakness in the final product. Remarkably, electric arc furnace technology allows recycled steel to be produced with significantly lower carbon emissions compared to traditional blast furnace methods. What I personally find fascinating about this stage is how solid industrial waste is transformed into a fluid material that can be precisely engineered. But what happens in the next stage is where the real chemistry takes place, as the molten steel is refined for strength and durability. Once the metal has melted, the liquid steel enters a refining phase where its composition is carefully adjusted using alloying elements and controlled gas injection. Engineers add precise amounts of carbon, manganese, and other elements to achieve the mechanical properties required for railway infrastructure. During this stage, impurities are reduced and the molecular structure of the steel becomes more uniform. Interestingly, even small adjustments in alloy composition can significantly influence hardness, flexibility, and fatigue resistance. In my opinion, this stage plays a critical role in determining the long-term durability of railway tracks under extreme mechanical stress. With the chemical balance optimized, the molten steel is now ready to take on a solid form with remarkable structural strength. The refined molten steel is continuously poured into water-cooled molds that gradually transform the glowing liquid into solid steel billets. This process allows manufacturers to produce long, uniform metal sections that serve as the foundation for railway tracks. Advanced cooling systems carefully regulate temperature changes to prevent internal stress or structural defects. Surprisingly, even slight variations in cooling speed can influence grain structure and impact overall material strength. What I personally find fascinating about this stage is how controlled cooling determines the internal integrity of the steel. Something unexpected is about to happen in the next stage, where immense mechanical forces reshape these billets into the recognizable form of railway rails. At this stage, the solid steel billets pass through a series of powerful rolling mills that gradually shape the metal into the precise geometry required for railway tracks. Each rolling stand applies carefully calculated pressure to form the railhead, web, and base structure. The process requires extraordinary precision because even small dimensional variations could affect train stability and safety. An interesting fact is that railway rails must withstand enormous repetitive loads for decades without significant deformation. In my opinion, this stage perfectly demonstrates how engineering accuracy ensures reliability in large-scale transportation systems. With the rail profile now fully formed, the next step focuses on ensuring that each piece meets strict quality standards before leaving the factory.
Seems consistent with the last batch, no significant defects.
Before the rails are approved for real-world use, each piece undergoes rigorous quality inspection using advanced industrial testing technologies. Ultrasonic sensors scan the internal structure of the steel to detect hidden cracks or microscopic defects that could compromise long-term safety. Laser measurement systems verify dimensional accuracy to ensure every rail meets strict engineering standards. Interestingly, railway infrastructure must withstand millions of repeated load cycles over decades of operation. What I personally find fascinating about this stage is how invisible imperfections can be identified using precise scientific instruments. The next step may surprise you, as the finished rails are carefully prepared for transportation across vast distances. After passing inspection, the finished railway rails are bundled and transported using specialized heavy-duty logistics systems. Overhead cranes carefully lift and position the rails to prevent structural damage during handling. These long steel components are then shipped to construction sites where railway networks are being expanded or maintained. Surprisingly, a single rail segment can weigh several tons, requiring precise coordination during transportation. In my opinion, this stage highlights the complexity of industrial logistics required to support global infrastructure development. As the rails leave the factory, they begin their journey toward becoming an essential part of modern transportation systems.
Utilizing advanced blue. This laser measurement system detects minute deviations across the entire rail profile.
Once installed, railway tracks play a vital role in transporting people and goods efficiently across long distances. From high-speed passenger trains to heavy freight transport, these steel rails support continuous movement that powers economic activity worldwide. The durability of railway steel allows it to perform reliably under extreme environmental and mechanical conditions. Interestingly, properly engineered rails can remain in service for decades with minimal structural degradation. What I personally find fascinating is how recycled materials can ultimately support critical transportation systems used by millions of people every day. This transformation demonstrates how industrial innovation contributes directly to sustainable infrastructure development.
Take it up slowly, clear the stack. Move left to the flat car, then easy down. Over.
Although railway tracks are primarily used within large transportation systems, proper engineering standards and maintenance practices are essential to ensure long-term performance. Regular inspection helps detect wear, alignment changes, or structural fatigue caused by repeated heavy loads. Engineers must follow manufacturer specifications and international safety standards when installing and maintaining rail infrastructure. Interestingly, even small deviations in rail alignment can influence train stability and passenger comfort. In my opinion, consistent maintenance plays a critical role in maximizing the lifespan of railway systems. Proper use includes ensuring stable foundations, controlled load distribution, and periodic monitoring to maintain safe and efficient transportation performance for decades to come. Thank you so much for watching all the way to the end of this video. If you found this production process interesting, please comment 1 below. If you think the video could be improved, feel free to comment 0 and share your thoughts. Also, tell me in the comments, what production process would you like to see in the next video? Your support truly motivates me to keep creating more industrial documentary videos like this. If you enjoyed this video, please consider liking, subscribing, and sharing it with your friends.